Okay, so now we move on to bits and bytes. Now if we start in base 10 denary, we have here a 1, 2, 3, 4 digit number. So we can refer to this as a 4-digit base 10 number, and that's because we're using the base 10 system for our place values and to dictate the number of numbers that we can use, 10 of them, 0 to 9. If we move on to base 2, here we have a 1, 2, 3, 4, 5, 6, 7, 8-bit number. Now this word bit is derived from, if we take the digit from base 10 and we essentially bring in the B, that gives us 1 bit, 1 binary digit. So here we have an 8-bit base 2 number. Base 2 because we're using the base 2 system to create our place values and only use the first two numbers 0 and 1. So when we are talking about quantities of binary, there are certain terms that we can use. So we've already mentioned that we have individual bits. Here we have 8 bits. 4 bits together are unofficially named a nibble. Now this is a 2 nibble number, but we don't usually call it that. What we call this, these 8 bits, is 1 byte. So we can have multiple bytes, 2 byte, 3 byte, 4 byte, but remember that 1 byte is 8 bits. So here we have a 2 byte number, or simply a 16-bit number. If we have a byte and then some extra, we don't refer to this as 1 byte plus whatever, or a byte and a half, or something like that. We just refer to the number of bits. So there's the byte plus the extra 5 bits. We call this just a 13-bit number. Now if we look in the spec, it says that we need to know what n bits can represent 2 n numbers means. So in this case, the n is just a variable, a placeholder. We could plug 3 into that n, which gives us 2 to the 3, we reuse that n. But if we have 3 bits, we can have 2 to the power 3 different numbers, or represent 2 to the 3 numbers. So if we place 3 bits in, there's our 3 bits, and we go through all the different combinations of flipping these zeros to ones and so on, we should be able to predict that we've got 2 to the 3, which is 2 times 2 times 2, 8 different combinations, which gives us 8 different combinations. All we're doing here is we're counting up in binary. If we increase the number of bits to 4, so 4 bits can be represented by 2 to the 4, n bits can represent 2 to the 4 numbers. So if we put our 4 bits in, and then we go through every combination, we end up with 2 to the 4, so 16 different numbers that we can represent. Here is 1 byte. It's the number 0. Here we have 50 bytes, all zeros. Here are 100 bytes. If we get up to 1000 bytes, then we can call this, using the base 10 system, 1 kilobyte. There's another way we can represent quantities of binary. If we add in another 24 bytes, we've now got ourselves 1 kibi byte, which we'll come on to in just a second. Okay, so when we are quantifying the amount of binary, we can use 2 systems. The more commonly used and more widely used is the metric system for this. Essentially, if we have 1000 bytes, or 1000 groups of 8 bits, we call this 1 kilobyte. Just note the lowercase k on this. If we have 1 million sets of 8 bits, or 1 million bytes, we call this a megabyte. And gigabyte, terabyte, petabyte, and so on. In the base 2 system, instead of using base 10 to quantify the amount of binary, we use base 2. So we have 2 to the 10, or 1024 bytes. We call that 1 kibi byte. If we have 2 to the 20, we have got 1 mebibyte. Okay, and there are just some of the other terms used to quantify in base 2. Thanks for watching.